This is lesson 26, example problem number 3. So we have a cantilever beam with a 10 pounds per foot uniform distributed load across the top of it, and it is 10 feet long. Asks us to solve for the reaction forces and then draw the shear and moment diagrams. All right, so first thing, solving for the reaction forces. If we go look at the wall, we should end up with a horizontal force, a vertical force, and then also a moment, or I guess to be consistent, that would be an A with a subscript of M, and we'll go ahead and define a positive direction of rotation. Okay, so remember, when you have a wall support, you have a X reaction force, a Y reaction force, and a moment at the wall. All right, as opposed to remembering pin supports have an X and a Y, and roller supports just have a Y. So that makes the cantilever beam, the beam attached to a wall, slightly more complicated. But this is a pretty easy problem, as we'll see. We do sum of the force in the X direction is equal to 0. The only force in the X direction is A sub X. Therefore, A sub X is equal to 0. Sum of the forces in the Y direction is equal to 0. And we have an AY. And then we have another one of these distributed loads, right? So we can go ahead and convert it to a point load for the sake of solving for our A sub Y and our moment, right? So if it's 10 pounds per foot and it's 10 feet long, therefore it's 100 pounds. And if it acts all the way from 0 feet to 10 feet and it's uniform, that means the equivalent point load acts in the middle at 5 feet. So draw that, 100 pounds, 5 feet. Okay, so AY minus 100 pounds is equal to 0. Therefore, AY is equal to 100 pounds. And then last one, sum of the moments is equal to 0. So things to watch out for on this one, right? Because this A sub M that the wall is providing in support is a moment already, it doesn't need to be multiplied by a distance. It's just a moment. So it's just A sub M, right? And then we have our A sub Y, that's 0 feet away. So that is going to cancel. And then we have our 100 pounds that's 5 feet away. And since that would provide clockwise rotation, that one's going to be negative. AY times 0 is 0. Therefore, our moment at the wall is 500 foot-pounds. Okay, so at this point, we've solved for all of our reaction forces. So we can move into doing our shear and moment diagrams. So like I said in the previous example, you have to remember to go back to having a distributed load before you do your shear and moment diagrams, or else it's all going to be wrong. So I'm actually going to not draw that there. I'm going to draw the distributed load first, which goes over the whole thing. Right, so that's 10 pounds per foot. And then at the wall, we have a positive 100 pound vertical force. Okay, so, and then I guess I'll draw it again on here. We have our 500 foot-pound counterclockwise moment at the wall as well. So first up is drawing our shear diagram. So we have shear, which is going to be in pounds. We have X, which is going to be in feet. So remembering back to how we said to do these, we're going to start at the left, and then every time we have a force, we're going to go up or down by that amount. Now, that 500 foot-pounds is a moment, so that's not going to affect our shear diagram. However, when we get to our moment diagram, it will affect it. So we do need to keep it there as something that is going to matter. It's just not going to matter for doing our shear diagram. So the first thing we have is we have our positive 100 pound force, which is going to take our shear from 0, jump it all the way up to 100 pounds. And then as we go across 10 feet, we have 10 pounds per foot of downward force. So in total, again, that's negative 100 pounds. So by the time we get all the way out to 10 feet, we have to have dropped back down from 100 to 0. So we just draw a straight line between the two. And that's that. That's our shear diagram. Okay. So next up is our moment diagram. So this is where it's going to get slightly complicated. So, boom. X in feet, moment in foot-pounds. Okay, so we start off and we have a 500 foot-pound moment. So that's just going to kick us from 0 all the way up to 500, the same way that the vertical point loads kick us up or down on the shear diagram. So we go from 0 up to 500. And then moment is the integral of shear. So we're going to take that area. It's a triangle, so the area is 1/2 times base times height gives us 1/2. The base, that's multiplied by, is 10 feet. The height is 100 pounds. Therefore, we have 500 foot-pounds. Awesome. So 500 foot-pounds. And it's above the x-axis, therefore it's positive. So we started at 500 foot-pounds. If we have a positive 500 foot-pounds, that would put us at 1,000 at 10 feet. So we go up and up and up and up. Well, that didn't work. So we look back at our rules for moments and shear diagrams, right? They have to start and end at 0. Well, we did everything right, but it didn't start and end at 0, did it? So something was wrong. And that something comes in with that 500 foot-pound moment at the wall. So this is where some of the sign conventions get really complicated, because there's one sign convention that you assign yourself, right, when you're solving for moments and you're solving for reaction forces. That's completely different from the sign conventions that are associated with shear and moment diagrams. So if you look at lesson 26, right, and go to, which slide is it on? Slide 12, it's going to show you positive bending and negative bending. Both of the earlier examples we did had positive bending, right? It bent the beam so that it looked like a smiley face. For a cantilever beam, right, that's sticking out from the wall, if you apply a bunch of forces to that cantilever beam, it's going to bend down, right? That's going to give it what's called negative bending. And the convention associated with negative bending is that the internal moment, what we're graphing on these moment diagrams, is going to be negative across the entire beam. Okay, so what does this mean for us when we're actually drawing shear and moment diagrams? So if you look at your shear diagram, your shear is positive across this entire beam. So if you do the integral of shear, you're going to get a positive 500 foot-pounds. So the only way for moment to start and end at 0 is if when you do that moment at the wall, you make that a negative 500 foot-pounds on your moment diagram. So what does it look like if we do that? Well, we take moment, x in feet, moment in foot-pounds. We start at 0, and let's take that negative 500 foot-pound moment at the wall, and then we gain 500 foot-pounds as we go from 0 to 10 from integrating our shear, which takes us from negative 500 back to 0. So now we have a moment diagram that does conform with the rules of starting and ending at 0. So I realize this is a weird convention. And remember, it has nothing to do with the convention of direction of rotation you assign when you're solving for reaction forces. It's solely a convention for drawing the moment diagram. So when you're doing these problems, go through the same way you've been taught, solve for your reaction forces, solve for that reaction moment at the wall, draw your shear diagram by going up or down as you find every force, and then just be careful when you're drawing your moment diagram. If you draw it the first time and it doesn't go back to 0, it's probably something to do with the sign convention on that internal moment. And if you flip that sign so that now it does start and go to 0, that's the way you do it right. So again, this right here is wrong. This is right. And then so we've got another example of a cantilever beam in the slides for example 6 as well, if you want to take a look at that. All right, thanks.